will be so disappointed.
Yeah, no, they asked me a couple of minutes back to start the streaming, and I said, yes, I will do that. Okay, let me
Written
check
that it is live streamed.
So is this Bhaskar behind Track B FSTTCS host?
So this is Prince from IT Goa. So the
Okay,
live streaming will happen in a minute.
Okay, good. Let me check. Is it already started by you? I see it appears, it disappears.
Yes, sir, it just started.
Okay, wonderful. Thank you.
Okay.
We'll start in 2 minutes.
Yeah, I see it appears, it disappears.
Yes, sir, it just started.
Okay, wonderful. Thank you. Thank you. Great. So we have no speaker yet for the third talk. Show up.
Then we just overrun with the first two. That's okay.
Yeah. So Anirban, I see you are here. Anirban?
Yes. Hi.
If the third speaker doesn't show up in time, I may ask you to switch and give the third talk, and then
Sure.
Okay, let's see, maybe they come. Okay. So welcome to the first session in the Track B of FSTTCS 2020. Our first guest today is Carolina Lehtinen, who will speak about the succinctness of alternating parity good for games automata. Carolina, the floor is yours.
Thank you very much. Thank you for joining us for this session. The work I'm presenting is joint work with Udi Boker, Denis Kupperberg, and Michał Szewczak, with Udi being my second in this session in case anyone asks any nasty questions. So when we work with automata, we have to choose what kind of automata we want to use, and there are usually trade-offs between automata models that are very simple, that have lovely algorithmic properties, such as deterministic automata, which are easy to complement and that compose well. So for example, if you want to change the acceptance condition of a game from an omega regular condition into a parity game, what you would do is you get a deterministic automaton that recognizes your winning condition and compose that with your game in order to get your parity game. So deterministic automata are useful for that kind of applications. On the other hand, they can be very large. So in contrast, more powerful automata models such as alternating automata can allow you to express the same properties but with a double exponentially smaller automaton. So we have this trade-off between algorithmic properties and representation size. So it's interesting to look at where exactly we get the sweet spots for those trade-offs. And good for games automata is one form of intermediate automaton that gives us an interesting compromise between algorithmic properties and succinctness. So good for games automata are automata that are not deterministic. So we allow for non-deterministic choices, or as we will, even universal choices. However, those choices are restricted. In particular, for good for games automata, we have to be able to resolve those choices without looking at the future of the input word. So we can't make choices that are based on things like will this event occur? Is this the last occurrence of this event? We have to make all our choices by looking at the past of the input and run so far. And this restriction allows our non-deterministic good for games automata to be used instead of deterministic automata in various applications, such as solving games, or pretty much anywhere where you compose automata. You can use good for games automata instead of deterministic automata. And already for non-deterministic good for games automata, you get an exponential, for some languages, you get an exponential succinct gap. So there are languages that are recognized by very small good for games non-deterministic automata that are not recognized by deterministic automata unless they are of exponential size. However, in this work, we look at alternating good for games automata. So alternating automata are automata where we have both non-deterministic choices and their dual universal choices. And these automata can also be good for games by requiring that both the non-determinism is good for games, so resolvable without looking at the future of the input, and the dual universal choices have to also be good for games. Also, they have to be resolved without looking at the future of the word, and that gives us alternating good for games automata. And these automata can also be used in all the same places as a deterministic automata, where so they have good compositional properties. We can use them instead of deterministic automata. And here in this work, we look at what are the gains in succinctness we get by allowing alternations in addition to non-determinism in good for games automata. And we show that we get an exponential succinctness gain. So in the same way as going from deterministic to non-deterministic good for games automata, there is an exponential succinctness gap. We also have one going from non-deterministic automata to alternating good for games automata. However, we also show that these two exponential gaps, they don't combine into a double exponential gap between deterministic and alternating good for games automata, as normal alternating automata do have are double exponentially more succinct than deterministic automata. This is not the case for good for games alternating automata, which are always equivalent to a deterministic automaton of exponential size. We also show that recognizing whether an alternating automaton is good for games is in X time, which matches the current best algorithms we have for recognizing whether a non-deterministic automaton is good for games. So in other words, in this paper, we show that by allowing alternations in addition to non-determinism in good for games automata, we do gain in succinctness without adding to the complexity of determinization or recognizing whether the automaton is good for games. We also briefly talk about automata where only the non-deterministic choices are good for games and the universality is arbitrary, which are already good enough for some applications. So we can checking whether all executions satisfy a property described by a half good for games alternating automaton is already quasi-polynomial, whether if that was an arbitrary alternating automaton, we would have an exponential, we would need an exponential to get rid of the alternations, which we don't need to do if half of our automaton is good for games. So we look at these half good for games automata and show that actually recognizing this half good for gameness is hard, is B-size hard, while we conjecture that recognizing whether the whole automaton is good for games, we conjecture that that might be polynomial. I'll stop there so that we have actually some time for the Q&A part of the Q&A session. Thank you.
Thank you, Carolina. Very nice. So we are open for questions.
I have a question.
Yes, please.
So your X-time algorithm for designing good for gameness, does it also include in particular solving the actual game, or does these X-times somehow accumulate, or?
So it does involve solving some games, but not necessarily the game you're thinking of. So for the deciding the good for gameness, we use the fact that these good for game strategies exist on both sides. We can use that to show that there is a strategy in a slightly different game that combines these two strategies, and which we can solve in next time. So yes, we solve some games, but have to be a bit careful exactly which one you solve.
Thanks.
Thank you. I also have a question while somebody else is preparing. So you mentioned that there are other products where good for games can be useful that are not necessarily solving a game. And I wonder, in such kind of applications, how do you, can you profit of this full good for gameness? I mean, I can imagine needs for solving the existential choices, but both existential and universal choices in something that is not a game application, this I would be wondering.
So if you want to change an alternating automaton that has some omega regular acceptance condition, if you want to change it into, say, an alternating parity automaton, then you would do that by taking the product with a deterministic automaton or a good for games automaton that recognizes the acceptance condition, which is very similar to solving a game, except that you have this additional, well, it's an automaton rather than the game, so you have inputs. But the same construction works there, for example. So changing the acceptance conditions of automata would be one application.
I agree, this is not exactly the same as games. I can follow this intuition indeed. Yeah, very nice. Thank you. Are there further questions? Sven, please.
So I would suppose that good for gaming an automaton is also doubly exponential, just like determinizing it, or is it not?
Sorry, so good for gaming. Yes.
So you get an alternating out.
Yes, so I see the question. I would expect yes, because yes, there are languages where the best you can do is the deterministic automaton. So if your good for games choices are, well, if your non-deterministic choices are very bad for games, so if they depend on, genuinely depend on the future, then the best you can do is to determinize. So I haven't looked at, for this, for non-deterministic automata, you have Tom Hensinger and Neil Peterman's paper who do this going towards a good for games automaton, which then in the worst case gives you a deterministic one. And I'm not aware of that having been done for alternating automata. But I suspect, well, yes, the theory says that you're not going to be able to cheat the determinism. Yeah. Thank you.
So I understand you have a way to construct automata that are not good at all for games.
Well, an intuition of if you have languages where the choices depend on the infinite behavior, whether there's an infinitely many A's or something like that, then good for games non-determinism isn't going to be helpful.
Thank you, Carolina. So if there are no more questions, we move on to the slides for the next talk. you. Perfect. We can see your slides. Your microphone is on.
If my microphone is off, that's an extra benefit.
So I will announce you only in like 2 minutes because everything went so smooth.
Yes, that's so unfair. Carolina puts the bar so high and I have to comply. This is not good.
So we stay in Liverpool, and our next talk will be also on Good for Games Automata, given by Sven Schewe.
Thank you, Dietmar. Thank you, Dietmar. So my talk is going to be so 2020 because it's for these old-fashioned non-deterministic good for games automata. Right, so the problem is that you want to, well, minimal is not quite true, of course, for a decision problem, that you want to have a small non-deterministic good for games automata of a given size. And you can look for Büchi, Co-Büchi, or parity automaton. You want, if you're given one of them, then you want to an equivalent good for games word automaton, right? And I don't have to say much about them because Carolina just spent the whole talk explaining what they do. These are non-deterministic automaton, which can just work with the past and not with the future. So they have non-determinism, but with a restricted power. So why would you do this? Well, it's for curiosity and it's for beauty, of course, but there are also some application in synthesis, in game solving, and even in model checking. So if you look at related problems, then of course, if you start with a deterministic automaton, there are quite a few things that can be done in polynomial time that are tractable. Of course, if you start with DFA minimization, but also if you start with a deterministic weak automaton, then you are in P. And also, it's quite interesting, if you have a transition-based good for games Büchi automaton, then minimizing that is also tractable. Right? And on the other hand, you have the big gap of a big bunch of p-space hard things like NFA minimization, NBA minimization, NPA minimization. There you are in the p-space region. And somehow for deterministic automaton, for Büchi, Co-Büchi, and parity automaton, you're in the middle, right? You're in NP. Right, so it looked very curious that if you add good for gameness, suddenly you are tractable. And the question is now: is this maybe because of the traces, and is this maybe using trace acceptance much better, right? So I'm going to try to squeeze into the short time how minimizing good for games Büchi automata, Co-Büchi and parity automata are very similar, is NP complete if you use state-based acceptance instead of using transition-based acceptance, right? For the NP part, it's just guess and check, and for the NP hard part, we can just borrow the hard languages that establish the NP hardness for deterministic Büchi automata, and I'm not going to talk about the generalization to parity and Co-Büchi automata, but they are not very difficult. And then I'm just going to mention why all this argument breaks down if you put the acceptance on the transition instead of putting them on the states. Right, so the inclusion in NP is quite straightforward. So if you are given a good for games automaton or a deterministic automaton if you want, and a bound n, right? Then you can ask the typical decision question: is there a good for games automata of a certain type, right? With up to n states or with up to n transitions, depending on what you look for. And here's, of course, a trick, right? I mean, somehow you must be given a good for games automaton, and the question of how expensive it is to check for an automaton whether or not it's good for games is open. But here the trick is, of course, that, well, if somebody gives you an automata which is not good for games, then you can answer what you want. So the sketch for this is quite straightforward. You can just guess a candidate, right, and then validate simulation in both directions, because an automata is good for games if and only if it simulates one or if it simulates all good for games automata, right? So in the original paper, it was if it simulates a deterministic automata, but replacing these things is quite straightforward. Right, and as you then have two parity conditions which are disjunctive, right? It's in NP to decide whether or not the simulation is there. I'll talk a bit more about the NP hardness part, right? And for the NP hardness part, you can use known reduction from the vertex cover problem, right? So you start with a nice graph, and the nice graph is just a connected graph with a particular starting vertex, which is somehow designated to have a starting point for a language. Right, and of course, the question of whether there is a k-vertex cover for such a graph is NP complete, right? And here is a minimal vertex cover for this small graph, right? And then you had just start with defining a language, which is kind of hard to figure out how big a smallest representation is. And this hardest language has two parts: a very simple one and a slightly more difficult one. The simplest one starts with assigning colors to the vertices, right? And then you add lots of self loops. And you have this particular letter, I read stop, right? And what you want is that when you see a stop, you move to an end node. And when you read a particular color, you try to go to the vertex of that color. So here, let me start with an example. If you see first this orange, right, you would try to move to the orange node, which works because there's a self loop. You see an orange again, another orange, and you see a green. You can move over there, another green, another orange, another green, a blue, a purple, another purple, a blue, another blue, and then you see a stop node, right? And when you see a stop node, you are in this in this copy of the node, and then you accept when you see this color again. And if you do not see this color again, then you reject, right? So this is what you do whenever you have one or more of these stop signs in the language, right? This word would be rejected because after reading the stop sign, right, you want to see a yellow, and that's the wrong color. And this word would be rejected because after this blue, you see a yellow, and there is no edge beside it, right? So you have a long word where you can either stay in the same vertex or move to an adjacent one, and after the first stop sign, you have to see the same color as you have seen before seeing the last stop sign. So these are the stop words, and it's fairly straightforward how to build an automaton, right? And if you want to build an automaton, of course, what you need is as many of these copies as you have vertices in your graph, and as many rejecting states over here, no matter what type of automaton you have, as you have vertices in your graph, right? It's easy peasy. Right. The tricky part of the languages here is those words which do not contain any of the stop signs, right? And you say, well, I would want to accept a word then, right? If you can still trace it in your automaton, right? In this graph, right? So that you only take self loops or move to adjacent vertices, but you also want to see infinitely many edges, right? Which just means you don't want to stall forever in one of the vertices. Now, giving any any automaton which would recognize such a word is fairly easy, because you could just add a copy for each of the vertices, right? And when you move over, you go into the accepting copy. When you stay, you go into the rejecting copy and stay there forever, right? However, you can do a bit better. You can just add one of the accepting vertices for one of the adjacent vertices of every edge, right? So this way, when you take any of the edges infinitely often, like this one, right? When you take it into this direction, you go to an accepting vertex. If you would take it in the other direction, there is no accepting copy, right? But that doesn't matter. If you take such an edge infinitely often, you will infinitely often go to one side which has an accepting copy, right? So as long as you have for every edge one adjacent vertex which has an accepting copy, you can build in this language, right? And this is exactly what defines a vertex cover, right? So by minimizing an automaton which recognizes this language, you get a vertex cover, and that's of course an NP-hard problem. And so you can exploit minimization of such a language for getting a minimal vertex cover. Or if you look at a given bound, right? I mean, if you have a k vertex cover, you have a 2n plus k automaton which recognizes this language. If you have no k vertex cover, you have no automaton of that size which recognizes this language. It's easy peasy. Okay, right. So a given nice graph with n vertices has a k vertex cover if and only if it's recognized by GBA or a DBA, right? So actually this is deterministic, but paper shows that being good for games doesn't buy you anything with 2n plus k states. Right, and this problem is of course NP complete in all combinations. Right, and just to close with a remark why this breaks down as soon as you move the acceptance to the transitions, right? If you ask the same question with a transition-based automata, it's pretty straightforward. You just make the edges that you can take accepting, right? And there is no question of how you produce this. You don't have to find the vertex cover. Coming up with an optimal transition-based good for games Büchi automaton is an absolutely trivial problem. You need 2n states, full stop. Okay, so to sum up, we've shown that good for games automata minimization is NP complete. And it's pretty much for the harder part that you can take a k connected vertex cover problem and reduce it to the question if you have a k plus 2n state good for games Büchi automata, but you can do the same thing with co-Büchi or parity automaton for the characteristic language that I had defined before. Right. And as it has a deterministic solution, if you look for an edge minimal automaton, it works just as well. Right. Okay. And you've also shown that it's NP. And well, if it's NP hard and in NP, it's NP complete. Right. But maybe transition-based problems have the edge. Right. I couldn't resist that pun. So as we know that a good for games Büchi automata minimization is tractable if you only put acceptance on the traces. So maybe this just points at using traces for acceptance is just a better choice. And of course, it's open what this means for co-Büchi and parity automata. And actually, it's also open what it means for deterministic automaton, where, of course, the same reduction had been used, and that also collapses if you put the acceptance on the traces. Thanks a lot.
Thank you, Sven. This was very nice. Do we have questions?
So a comment and a question.
Yes, please, Udi.
So this Sven notion of G something, GBA, GPA, is very nice, but it seems that it doesn't work for telling whether it's non-deterministic or alternating. the automaton that is good for games. So I guess we'll need to find some other shortcut.
Oh, I see. Yeah, but as I said in the beginning, this talk is so 2020. In 2021, of course, nobody is going to use this automata any longer now that you have introduced the successor class.
No, they should use, but yeah, but with some name.
I find this very appealing because there is a whole discussion about what a transition system should tell. What happens in a state or what changes when you go from a state to another, like action-based or state-based descriptions and so on. And here, I mean, this is a very accessible example where all the combinatorial intricacy is gone when you move from actions into states. No, the other way around. Huh? And I mean, this is the only technical argument that I have seen in this discussion so far. I know that you're not part of the discussion.
It's true.
Yeah.
But it also it opens the new questions again. Right? So if anybody wants to see if a transition-based deterministic parity automata a minimization is cheaper, it may well be. Who knows?
Do you have a conjecture about that? If you had to bet, which side would you land on?
I know you love your bets, right? But I don't really have one. Although now that you are moving to France, knowing your histories, we actually start to collaborate, and that might be a starting point.
Thank you very much, Ben. So
I have a question.
Yes, one more quick question. Yes, please.
Yeah. So can you get some results on approximate minimization using reductions between the transition-based acceptance and state-based acceptance?
Well, I mean, if you look at Büchi conditions, of course, there is only a blow-up of 2, right? So if you have a transition-based minimization and you move to states, then you can use the crudest way of generalizing, and you will not have a blow-up of more than 2.
Right. Cool. Thanks.
Thank you, Sven. And we move away from Liverpool and we go to Jerusalem. So our next speaker is Noam. Noam, are you there? Okay, the slides are here.
Yes, I'm here.
Oh, welcome. Nice to meet you. So it is about perspective games with notification, joint work with Orna. Please, Noam.
Thank you. So we are going to talk about perspective games with notifications. Our motivation is the problem of reactive system synthesis, which is the task to construct a system that satisfies a given specification for all possible behavior of the environment. We can model the interaction between the system and the environment as a 2-player zero-sum game, where a winning strategy for the system corresponds to a transducer for the given specification. The game is played on a graph, where the vertices are partitioned between the players, and each vertex is labeled by an assignment to the atomic propositions. So in this example, the circles are vertices controlled by player 1, the squares are vertices controlled by player 2, and the set of atomic propositions is P, Q, sharp, and $. Starting from an initial vertex, the players jointly traverse an infinite path in the graph. This is done by each player choosing the successors of the vertices she controls. This infinite path is called a play, and the word that labels the vertices of the play is the computation induced by the play. So for this example, assume that player 1 always chooses VP as V sharp successor, and that player 2 always chooses UQ as V $ successor. Then the generated play is V sharp, VP, V $, UQ omega, and the induced computation is sharp, P $ Q omega accordingly. The objective of player 1 is given by a language L over the assignments to the APs, and we say that player 1 wins if the induced computation is in L. For example, consider the objective given by the LTL formula psi, which equals to whenever there is a $, and in the next position there is a P, then 3 positions afterwards there is also a P. and whenever there is a $, and in the next position there is a Q, then 3 positions afterwards, there is also a Q. In our game, a computation is inside if every time player 2 chooses UP as V$ successor, then player 1 chooses VP as V# successor right afterwards. And whenever player 2 chooses UQ as V$ successor, then player 1 chooses VQ as V# successor right afterwards. So player 1 can win with the objective psi if she will follow this exact strategy. The example we just saw, the players have full visibility, which means they can see visits in the other player's vertices and choose successors based on this information. There are many settings, though, where the players cannot observe the entire evolution of the computation. Previously, 2 models of partial visibility were introduced: partial observation games and perspective games. Partial observation games model settings where the players have a partial view of each part of the system, while perspective games model settings where the players cannot observe at all parts of the system they do not control. The example we see here illustrates the difference between the full partial observations and perspective visibilities. In the left, we have full visibility, and so the players have full view of each vertex in the play. In the middle, we have partial observations visibility, and so the players have a partial view of each vertex in the play. And in the right, there is perspective visibility, and so the players have full visibility in their vertices, but they cannot see at all vertices of the other player. Recall the game we saw earlier and assume it is a perspective game now, which means we now assume that the players cannot see visits in the other player's vertices. So now, player 1 cannot win with the psi objective we saw earlier because she cannot distinguish between a visit in UP and a visit in UQ, so she cannot choose a successor for V# based on this distinction. So now the review of previous work is done, and we can talk about our work in this paper. In many perspective settings, the players indeed cannot observe the evolution of the computation in parts of the system they do not control, yet they may have information about events that happen during these parts. We propose an extended model called perspective games with notifications, where the players cannot see visits in the other player's vertices, but they can receive additional information about events happening in them. In a perspective game with notifications, there is a finite state machine called an information satellite. The information satellite is executed during the play by updating its state according to the current vertex or its label, and it may notify the players with information by outputting various information signals called notifications. So now players can base their choices on both visits in their vertices and notifications they received in the past. Consider the following perspective game with the objective given by the LTL formula psi, which equals to whenever there is a Q and in the next position there is also a Q, then 3 positions afterwards there is also a Q, and whenever there is a Q and in the next position there is a P, then 3 positions afterwards there is also a P. In order for player 1 to win, 2 conditions must be satisfied. The first is that whenever there are consecutive visits in UQ and WQ, then the successor of the immediate visit in V# is VQ. And the second one is that whenever there are 2 consecutive visits in UQ and UP, then the successor of the immediate visit in V# is VP. It's easy to see that player 1 cannot distinguish between those cases since she cannot see visits in UQ, WQ, and UP. So player 1 cannot win with the psi objective. Now assume it is a perspective game with notifications about visits in the vertex WQ. Visits in WQ do distinguish between consecutive visits in UQ and WQ and consecutive visits in UQ and UP. So now player 1 can win by choosing VQ as V# successor if a notification was received, and choosing VP otherwise. So now we are going to present the system-winning decision procedure, namely how can one decide if the system wins the game or not. So first, consider a perspective game with notifications, where G is a graph, A is a specification automaton, and I is a satellite. At the beginning of the play, the objective of the system is to generate a computation that A accepts, starting from the initial vertex and the initial states of the specification automaton and satellite. As the play progresses, the objective of the system is updated. If the current vertex and states are V, Q, and S, then the current objective of the system, denoted by the tuple VQS, is to generate a computation that AQ accepts starting from V and S. If V is owned by the system and V prime is a possible successor for V, we denote by S, VQS, V prime the set of objectives that must be satisfied in order to fulfill the VQS objective after moving to the successor V prime. If V is owned by the environment, we denote by S, VQS the set of objectives that must be satisfied in order to fulfill the VQS objective for every possible successor of V that the environment might choose. So now we are able to define a strategy for the system and how we can decide if there is one. So strategies for the system can be viewed as infinite trees with branches in V1 union I labeled by V union a special character, where V1 is the set of the system's vertices, I is the set of the satellite's information signals, and the special character stands for no successor. Each node in the strategy tree corresponds to the system perspective of a prefix of the play that ends with either a vertex of the system or a notification. If a node corresponds to a vertex V of the system, then it is labeled by the successor assigned to V by the strategy. But if a node corresponds to a notification, then that notification must have appeared in a vertex controlled by the environment. Thus, the system cannot choose a successor in this case, and so it is labeled by the special no successor character. So now we can build a universal Kabuki tree automata that accepts winning strategies for the system. So the state space will be V time Q time S, where being in a space VQS corresponds to the requirement that the VQS objective will be fulfilled. So now if the automaton is in state VQS and reads V prime, it sends copies to all the states that corresponds to the appropriate set of updated objectives. And that way, if one of those objectives is not satisfied, then the automaton will reject the strategy as it should. The size of the automaton is polynomial in the sizes of the graph, specification automaton, and satellite. And although usually deciding the emptiness of universal automata is exponential in the size of the automata, since in our case the graph and satellite are deterministic, then deciding the emptiness of our automaton is polynomial in the sizes of graph and satellite, and exponential only in the size of the specification automaton. So deciding whether the system can win or not amounts to finding out whether the automaton that accepts winning strategies for the system is empty or not. So this is all for now, and if there are any questions, I will be happy to answer.
Thank you, Noam.
Thank you.
Hello. Jam, you look like you could ask a question.
Okay.
Please.
Yeah. The question is, sorry, how is the state space of the satellite? I mean, how does it compare with the state of the game? I mean,
that's a good question. So the satellite can either notify about structural events like visits in some vertices, or behavioral events like if some natural language, if some regular expression was occurred. So if the satellite, if the events we want to report about are structural, the state space of the satellite will be like the state of the game, because we will follow along the play. So we will follow along the vertices of the play. So it will be up to the size of the game plus maybe a constant. If it is a behavioral satellite, it depends on the condition, on the behavioral condition that we want to notify about.
Can we get away with a constant size satellite for some winning conditions? Or?
Yes, if we want, for example, a simple example, if we want a satellite that works as a clock. So we want to know how many rounds were played between each visit in our vertices. So a clock can be a satellite of size 1 that notify the players after every round. This is a satellite of size 1.
Thank you.
Thank you. Further questions? So maybe I have one more question. So you probably know about distributed synthesis, when you would have 2 players and then there is some environment and they have a common goal. Now imagine that one of the players doesn't know what his partner does, the other player doesn't know what he does. Environment is in this. Can you imagine that in your setting this problem becomes approachable? Because in general it's undecidable, but here you...
If I was to guess, I will say it's not. It won't work in our settings also, because if the players don't know, if the 2 players that want to act as a coalition don't know what the other player does, it will be a problem. This is my guess.
Maybe Sven has an intuition about this. I mean, it may depend on the satellite, but for example, if all the intersection points, I mean, whenever I give you control, I know where I am, I know what you receive, and then it's your part that you do, and then when you reverse the control, we both know again. I mean, that's a simpler restriction. So if we know the endpoints of transitions, we may get out.
I would concur with Noam. I wouldn't see what you can do if you don't see what happens on the other side. Of course, you're right. If your monitors give you, if your satellites give you full information, if they are good Israeli military-grade satellites that observe everything, right, then the other side is a bit hard pressed. But then it's not really distributed, and then maybe that's not a fair comparison.
Right. So we have new challenges. Thank you, Noam.
Thank you.
And so we move to the last talk, and we're perfectly in time. Anirban, if you want to share your slides.
Yes. Are the slides visible?
Yes, perfect, wonderful, and we can hear you. So Anirban will speak about synthesizing safe coalition strategies, and this is joint work with Nathalie Bertrand and Patricia.
Yes, thanks Ditma. So I am Anirban. This is a joint work with Nathalie Bertrand from INRIA REN and Patricia Boyer from LSV. So I'll talk about synthesizing safe coalition strategies. Let me start with a brief introduction to two-player concurrent games and graphs. So here we are given a graph as input and a finite set of actions sigma. Then the game, and we have 2 players. Now the game proceeds as follows. So the game starts at initial vertex, for example, here at V0 denoted with this red dot. And then the players choose their actions simultaneously. So, and next vertex is determined by their chosen actions. So what happens here, for example, if the player 1 chooses B and second player chooses A, then the game will go to V1. So similarly at V1, if first player chooses A, second player chooses B, or vice versa, then it goes to V2 and so on. And we say player 1 wins the game if he or she can ensure his win against any strategies of player 2. Then we can look at winning objectives such as reachability, safety, etc. So we are interested in extending this to parameterized setting, where parameter is the number of players. So here again, we have a graph and a finite set of actions, but now the edges are labeled with regular languages and number of players is unknown a priori. So the game proceeds as follows. It again starts at initial vertex. Now adversary fixes some k at the beginning, which is unknown to the player. So this k is the number of players. And then these players will choose their actions. This will form a word W. And next vertex is chosen accordingly. So if there is any non-determinism, for example, if this W belongs to more than one language, then the non-determinism is resolved by adversary. So for example, here, if W is in L3, then the game goes from V0 to V1 and so on. So we are mainly interested in this problem where arbitrarily many players are trying to achieve a common goal. And in this work, we are interested in safety property. So to formally define that, so this is a parameterized concurrent game arena. We define a strategy of player I as a mapping from sequence of vertices to action. Then a coalition strategy is nothing but an infinite tuple of sigma is, which we equivalently can say that it's a mapping from V plus to a word in sigma power omega. And we usually, as usual, define outcome as, so out of k v naught sigma tilde is set of outcomes induced by this strategy sigma tilde from initial vertex v naught when there are exactly k number of players. And we are interested in, as I said, safe coalition problem. So coalition wants to keep the play within a safe set of vertices. So formally, input is an arena, an initial vertex, and a set of safe vertices. And we say output is yes if and only if there exists a strategy such that for any k, the outcome is within the set of safe vertices. So in this work, we show that this problem is indeed decidable, and it's in X space and V space hard. Also, if there exists a winning strategy, we can synthesize that strategy in exponential space. So in this short talk, I'll mainly focus on, I'll give a brief idea about this exponential space upper bound. So how do we, okay, before going to there, let's just see an example. So in this example, we can show that players have a winning strategy, coalition winning strategy. So at this vertex, they play A, B, A power omega, because any other choice from here will lead to non-safe vertex for some k. Now, when they play A, B, A power omega, the game can go to, the history can be V0, V1, V2, V1. In that case, they know that there is exactly one opponent. So they can, so at V1, he has a choice, they have a choice. So they can play B power omega or any word in B sigma power omega, so that the game again goes to V0, and from V0, they choose the same strategy. And if the strategy is, if the history is V0, V1, then they note that there are at least two players, so they play accordingly, and they choose this part, they choose A power omega, or A power omega, sorry. So to solve this game, we first reduce this to a finite tree. So this is just an unfolding of this game graph, and yes, so levelings of this tree are exactly the levelings of this game graph. And we terminate a branch if something repeats along a branch, or any non-safe vertex appears. The idea behind this stopping criteria is that if a vertex repeats in this game, then the coalition may take the same strategy, and if it ensures safety in the first occurrence of that vertex, then again for the later occurrences also it will, the same strategy will keep it safe. So, and we can then show that we have a winning strategy here if and only if the coalition has a winning strategy here. Now it remains to solve this game, and since this is a finite structure, we can decide the game on this structure. So let me just briefly describe the idea. So we define a coalition strategy on a tree as a mapping from internal nodes to a word in sigma power omega. So this is equivalent to saying the strategy is an m tuple of omega words, where m is the number of internal nodes, and this can also be written as sigma m power omega. So this is a omega word over this tuple sigma power m. So now we construct a safety automaton over this alphabet sigma power m that accept words corresponding to winning strategies. So this is basically an automaton which runs automata for the languages over the edges. So a state corresponds to a state in B will correspond to different branches, and we say that a state is accepting if all the corresponding branches are safe. And we can show that coalition has a winning strategy in this tree if and only if so this language of this automaton is non-empty. So the size of this automaton can be double exponential, and it just remains to find find non-emptiness of this automaton. So we can show that this problem is indeed in exponential space. So yeah, just before to conclude, let me show an example. So this is the tree from the previous slide, and these are the languages. So a state of the automaton we want to build looks like this. So we have a component for each of the edge. So for example, here first component corresponding to this first edge, and second one for this edge, and so on. So I have denoted this cell corresponding to these three edges corresponding to the first node, and so on. So this will read a word in sigma power m, and so the first cell will read the letter in first component, and so on. And so P naught reading A remains at P naught, and so on. And then we can map a state with several branches. For example, this node here, we can see that we can map this state with this branch, which is safe. So we denote it as green, and we expand. So note that one state can correspond to different branches. So we only say this is a green state if both of them are safe, and we continue. And we see that here we have a safe path, which actually corresponds to a winning strategy in this example, which I have shown before. So yeah, just to conclude, we have shown in this paper that safe collision problem on this parameterized arena are decidable in exponential space. So this is done by reducing this problem to a finite tree unfolding and then checking on emptiness over of a double exponential size automaton. We have also shown in the paper that this is p-space hard, and we have also shown that synthesizing a winning strategy, if there exists one, needs exponential space. So future work, we are mainly interested in looking the same same kind of decision problems, but for reachability objectives. So here what happens is that we can have complex strategies for reachability. So let's look at this example. So here it's A star B A plus, but this is, so we the coalition wants to reach V1, whatever be the number of players is, and they can do this only if the last player plays B, but they do not know how many players are there. But they have a symbolic winning strategy in the sense that at first round, first player will play a B and others will play A. So they will play the word B A power omega. If there is only one player, then the game immediately goes here. Otherwise, it loops. And the coalition infers that the number of players is not one. So in the next round, they will play A, B, A power omega. So, and similarly, so whatever be the number of players, for example, if this is K, then at kth step, the coalition can ensure to reach V1. So yeah, we are mainly interested in looking at this problem in future, also to see if we can close this bound for safety condition. That's it. Thank you.
Thank you, Anirban. Do we have questions? Jam, please.
Yeah. Okay. That example that's there, oh, sorry, the slide that is in the last one that you were just talking about, you were talking about in the context of a bound. So does it also suggest that it's a problem with the tree unfolding technique, basically? That,
so do you mean for the reachability?
Yeah. No, the one above. No. There is the second example. Yeah, the reaching V1, right?
Yes.
I mean, the last agent.
Yes.
Yeah.
So for reachability, we cannot really apply the same technique because here, for safety, we have we can argue that if you reach the same vertex, you can take the same strategy. But here, it does not happen. Like even if you loop at the next step, you take different strategy. So the tree unfolding won't be finite.
Right. So that's one of the question. That tree unfolding technique is not going to work for other objectives.
Well, yeah, not at least for reachability, or also not and so on. Yeah.
Okay. Thank you.
Thank you.
So I have a question.
Please.
And it seems that in the model, if you have, once you fix the number of players, each player knows which index it's on, right?
Yes, we assume that every player knows its index.
So have you considered the model where this doesn't happen, where the players are just, they don't even know which indexes they're on?
Yes, well, no. I mean, we have not looked at it, but yes.
Because it seems slightly counterintuitive that they don't know how many players there are, but once there are a number of players, they each know where they're on. It's a weird sort of partial information. But fine.
Yes, I see.
Future work.
Yeah. Sure.
So there may be a related question. For safety, you have recognized that the strategies that you will construct, they are connected. I mean, at least by the fact that in the same position, everybody does the same thing. So they are not arbitrary tuples of strategies. So maybe connected to Shaul's question, how would it be if you would say, I want to synthesize a bucket of strategies, and whoever comes takes a strategy out of the bucket, plays it, and it will go well. No? I mean, in the simplest case, it would be just one strategy in the bucket. Everybody has to play it. I mean, that would be probably simple to do. But if you would have, I mean, well, some rule to give out strategies anonymously. So you take a strategy, it doesn't. You don't know your index, but maybe the distribution of strategy will guarantee that. Say if half of the people play this and the other half play that, then it will be fine.
See your point.
I mean, in this case of safety, you have a connection. You can say the strategies will be made in such a way that like they have to agree in the nodes. So we look at this subset. In the bucket, we will always find this kind of strategies. I mean, maybe the restriction is there anyway.
Probably, yes.
So we have 20 more seconds for asking questions. And as there is a gather town that has been set up, I will ask one of the organizers to paste us the link. Shantanu, could you paste us the link for the gather town? I'm not sure we all have it. If not, I try to improvise. Check. So
I can paste the link.
Oh, great. Thank you. Oh, perfect. So from Sunil, we got the link. And there we can meet and talk. So this will be the end of the session. Thank you very much to the speakers and to the audience and for all the questions. And see you in Gathertown then. And
thanks.
Bye-bye.
Hello. Okay. I see here Rishi. Yeah. Okay. Hi, Rishi. Yeah. So you're going to be first, right?
Yeah.
Okay, good. Then Peter, I guess.
Hi.
Hi. And then next will be Holger.
Yes. Hello.
Hello. The next after that will be Rebecca, I guess. Is she here? At least the talk was by her. So far, I don't see anybody from the fourth talk. And then there will be, I guess, Cyan. Cyan, you will be here next, right?
Yeah. Hi.
Hi. Okay.
Hi, yeah.
Good. Good. Okay. That's good. Okay. So we will take questions at the, I think at the end. Meaning after your talk, we won't take a question during the talk because we don't have much time. So let's wait for, so I guess Rebecca is here. Good. So we have a speaker from each of the paper. By the way, my name is Rohit. I'm going to chair this session. And let's wait. So does anybody know
Rohit,
if
thanks for waking up.
yeah, it's okay. I really wake up at this time. So my question
Okay.
is, if somebody sends a question on Slack, would they appear here or I have to be on Slack?
Technically, we are not taking questions from Slack, so it's fine. We can
Okay.
take it on Zoom. So everyone is on Zoom.
Okay, on Zoom.
So all the participants are on Zoom. So you don't have to worry about Slack. So it's mostly for the technical support. If something doesn't work, then there is a technical help always available on Slack.
Okay, good. Okay.
Yeah.
Good. Thank you.
Yeah.
Okay.
So we also have a gather
thing, yeah. But is it?
So there are some people there, so they might just come in a
couple of
minutes. Yeah.
Yeah. Let's wait.
May I start?
Okay. So let's start the session so that we can be on time. So our first speaker is Rishi, who's going to speak on static detection for Rtos applications. So once again, we'll let the speaker finish the talk before we take questions about the talk. Okay, go ahead.
I hope my screen is visible.
Yes, it is for me.
Okay.
Hopefully for others also.
Hi everyone, I'm Rishi Tulsian. Today I'll be talking about static race detection for real-time operating system applications. This is joint work with Rekha Pai and Deepak D'Souza at Indian Institute of Science, Bangalore. So the definition of data races we use is from Chopra et al. In ESOP 2019. So if we have two threads A and B in a program P, and two statements S1 and S2 under consideration, we add two skip statements immediately before and after S1 and S2. And then we say that if these blocks can overlap in some execution of the program, then an S1 and S2 are said to be in a data race. Of course, S1 and S2 are obviously read-write accesses to some shared variables, and then they can be in a data race. So Rtos applications, they consist of tasks and ISR threads, which are scheduled based on preemptive priority-based scheduling, and equal priority tasks, they execute in a round-robin manner. Interrupts are serviced immediately when enabled. So let's look at a very simple Rtos application. Here we have two tasks, A4 and B2 defined in the system. The main thread, it creates an instance of A4 at a priority 4 with ID T1 and an instance of B2 at a priority 2 with ID T2. And then it starts the scheduler. Since A4 is the highest priority task in the system, A4 starts execution first. It resets the value of X and then it delays for 10 time units. When A4 delays for 10 units, B2 can execute and B2 execute, but B2 can only execute for 10 time units, as after 10 time units, A4 is ready for execution and A4 is at a higher priority. So A4 will preempt B2 and this cycle goes on and on. Let's look at another demo application with some synchronization mechanisms. So in this system, we have two tasks, a producer task and a consumer task, and we have two shared variables, item and count. The main thread creates an instance of the producer at a priority 1 with ID T1 and an instance of the consumer at priority 1 with ID T2. And then it starts the scheduler. Since both producer and consumer are created at equal priorities, any one of them can execute first. Whenever the producer executes, what it does is it suspends the instance of the consumer using the ID T2, and then it goes ahead and accesses the item and the count shared variables. Once it is done with its access to the shared count variables, it resumes the consumer task. When the consumer task runs, it goes ahead and directly accesses the item shared variable, and then it changes its priority to a higher level, that is 2. And then it accesses the count shared variable, and then it changes its priority back to its original level 1. So here we can see that when the producer accesses the item and the count variables, the consumer task is suspended and the consumer task cannot preempt the producer task. Similarly, at line number 23, when the consumer task runs, it is running at a priority 2 and it is the highest priority task in the system, since the producer task is at priority 1. So at line number 23, the producer cannot preempt the consumer. However, at line number 21, the consumer is still running at a priority 1 and the producer is also running at priority 1 and the producer is not suspended. So when the consumer is running line number 21, it can still get preempted by the producer. So we can see that in this example, there are a variety of non-standard synchronization mechanisms like suspending other tasks and changing the priority of a task used for synchronization. In this example, the consumer task uses this null to signify that it is changing its own priority. What is also possible that the consumer changes the priority of the producer using an ID T1 here. In that case, until the consumer changes the priority of the producer, it will all these statements will continue running at a priority 1. And when the consumer changes the priority of the producer, let's say to some value 3, these statements can also run at priority 3. So we also see that each statement in the program can run at multiple dynamic priorities. And we use a range of minimum and maximum dynamic priorities to signify the range of priorities at which each statement in the program can run. So now we see that when the producer accesses the item and the count shared variables, the consumer is suspended. And when the consumer accesses the count shared variable, it is running at the highest priority. So line numbers 13 and 23, these accesses are race free. They cannot overlap with each other in any execution. However, since 21 is running at a priority 1, what might happen is 12 can the line number 12 can run while line number 21 is running. Hence 12 and 21 are not race free, and we would like to statically determine these facts and say whether whether two conflicting accesses are race free or not. So that is the problem we want to solve. So towards that, we define an occur in between relation between two statements, where if we have S1 in some thread A and S2 in some thread B, we add a skip statement immediately before S1 and immediately after S1. Now we say that if in any execution, S2 can run sometime after S1's leading skip, but before S1's trailing skip, then S2 can occur in between S1. So it is quite clear to see that if S1 cannot occur in between S2 and S2 cannot occur in between S1, then we can safely say that S1 and S2 are race free. So we give 6 patterns using these non-standard synchronization mechanisms when two statements S1 and S2 can be said to be race free, can be said to be not occurring between each other. So the first one is when the S1 is in some task A which suspends task B, and S1 is running at a minimum priority P1. We also require that there is no other task in the system with a maximum priority greater than equal to P1, which can resume B before A resumes B. So in such a case, we say that S2 cannot occur in between S1. This is the first pattern. Similarly, we have 5 other patterns where we say that statement S2 cannot occur in between statement S1. So let's revisit that example with these rules. And we see that at line numbers 12 and 13, we have this information that the consumer is suspended at line numbers 12 and 13. And there is no other task in the system at a priority greater than equal to 1, which can resume the consumer. So we say that the access to, and this is with respect to line number 23 and line numbers 13 and 23. So we say that line number 23 cannot occur in between line number 13. Conversely, when we look at line numbers 13 and 23, the other way around, we say that line number 23 is running at a minimum priority 2, which is the highest priority task in the system, and there is no other task running at a priority greater than equal to 2. So we also say that line 13 cannot occur in between line 23, and hence 13 and 23 are race free. However, at line numbers, when we consider the pair 12 and 21, we can say that 21 cannot occur in between 12, as again the consumer is suspended at line number 12 and there is no other task at a priority greater than equal to 1 which can resume the consumer. So 21 cannot occur in between 12. However, when 21 is running, it does not satisfy the priority condition. It is running at a priority 1, and there are other tasks in the system which also run at priority 1. So 12 can possibly occur in between 21, and hence we cannot declare 12 and 21 to be race-free. So this is a block diagram of the analysis. We use a combination of some pre-analysis like priority analysis and log set analysis to determine these priority and suspend facts at each point. And now, given any pair of conflicting accesses, we apply these 6 patterns to say whether two statements cannot, whether the two accesses cannot occur in between each other. If we are able to safely say that the two accesses cannot occur in between each other, we declare them to be race-free. So we implemented our analysis as a pass in C intermediate language, and we ran it on some demo benchmarks from NXT-OSIC, FreeRTOS, and Arduino Pilot, which are different real-time operating systems. And we found that our analysis is quite precise and efficient when compared to previous work by Schwartz et al. And Chopra et al. And so in conclusion, I would like to say that most previous work focuses on a limited set of synchronization mechanisms, but we propose an analysis which is quite comprehensive in respect to the synchronization mechanisms considered, and it is widely applicable to a range of interrupt-driven applications. So we would like to test our analysis on some real-world applications in the future. Thank you.
Thank you, Rishi, for the talk. So if somebody has questions, they can either raise their hands or put that in the chat. So, okay. So I actually have one question for you, Rishi.
Sure.
So you had so you said that your analysis is precise. So I guess that means you have less false positive typically than the other examples.
Yes.
Do you know why is that the case? What is the intuitive reason why you have fewer false positive?
Yes, so the reason is that these patterns that we proposed, they consider a wide variety of synchronization mechanisms, non-standard, and which consist of some non-standard synchronization mechanisms like suspending other tasks, dynamically changing the priority of either the self task or other tasks, and other standard mechanisms like flag-based synchronization, log-based synchronization, which are used in other analysis. So since we capture these non-standard synchronization mechanisms, that is why we are able to eliminate false positives in a better manner.
So they don't cover so many synchronization mechanisms. Is that the reason?
Yes, that is correct.
Okay. Okay. Thank you very much, Rishi.
Thank you.
I guess nobody else asked a question, so let's go to the next speaker, which is Prakash or Peter, who's going to speak.
So yeah, it's me.
Hi, Peter. Yeah, hi. A framework for consistency algorithms. The talk on YouTube was by Prakash, so I was just wondering if it will be you or Prakash. Okay, go ahead.
Okay, I have to check whether I'm able to share my screen.
You should be. You are the co-host, so.
So can you see it?
No.
Okay, so. Okay, maybe I have to change my browser. I had the same problem yesterday as well.
Okay, sure.
So just give me a second. And then...
Sure, no problem. So I wonder if we should go to the third speaker while Peter is figuring out his.
We could do that. Holger is online.
Here.
Yeah, so it's okay.
Holger, shall we start, Holger, and then?
Okay for me. Yeah, I can start.
Okay.
Yeah. Just give me a second to share the screen.
Okay.
Just the video.
Okay. Yes, we can see. Okay, so we'll go to the third talk and come back to second talk later on. So talk is on computable analysis for verified exact real computation by Holger.
Yep. So thank you very much for the introduction. And so my talk is about computable analysis and verified exact real computation in COG. And this is joint work with Mika Konechny and Florian Steinberg. So let me start, if I can. Yeah. Okay, so let me start by talking a little bit about our background, where we come from. So all three of us come from an area called computable analysis, which is kind of an extension of classical computability theory to uncountable structures from mathematics, specifically from analysis, like, for example, real numbers and real functions and so on. And well, classical computable analysis uses the Turing machine model to discuss computability and complexity of such objects. So typical questions in this area are what kind of problems can be computed in principle, for example, by using Turing machines, then using complexity theory, which of these problems can be computed efficiently, and so on. And in this area, we also consider not only real numbers, but also some spaces of spaces of continuous functions and other uncountable spaces from analysis. However, the model is so the model used in computable analysis is not only theoretical. It's kind of because it's based on Turing machines, so it's kind of a realistic model of computation. So it can, in principle, be implemented as computer software and software. So some people work on such software, which is called exact real computation. So this is, for example, so this is software that does numerical computations in real numbers without any rounding errors. So exact computation on real numbers. And this is the background. This is where we come from.
Holger, can you make your presentation full screen, because
it should be
because it's going to cut.
Oh, okay. Sorry. It should be full. So I went to full screen and I'm sharing. Is it better now?
Yes.
But no. Okay, sorry. No, it's come, I guess.
But it's still not full screen, right?
Yeah. So I had full screen. So okay, let me switch to full screen again. Is it better now?
For me, it's okay. Yeah.
Can you see the whole stuff?
So I think if you click on that little triangle midway down that gray bar, you'll get rid of that right margin, which is what is eating up some of your space. That says export PDF and edit PDF and create PDF and stuff like that.
Oh, okay. So this export PDF, edit PDF, create PDF that you see is.
No, so if you go down, there's a little triangle to the left of Adobe PDF pack convert files. I think if you click on that, then that whole margin will disappear.
So I see my slide in full screen, so I don't have to see.
You see? Oh, you don't see export PDF edit the.
I see my slide. I see my slide. I see only my slide in full screen.
Ah, okay. So we have different.
You're doing some mirroring, is it? Maybe that could be a reason. But anyway, maybe it's fine. We'll just continue.
Maybe let me just share again.
Maybe just show the slides.
Yeah, if that's better, I will just. How is it now?
That's better. That's better.
Yeah,
oh,
now it's fine.
It worked.
Now it's perfect.
Now it's fine. Now it worked. Yeah.
Just
now it worked. Yeah. Okay.
Okay. Yeah. Sorry. But I will just go on from this point, right?
Yeah.
Okay. Yeah. So let me go on. Okay, so this is kind of our background, and what we are doing recently is we are implementing some of the theory from computable analysis in the Coq proof assistant. So we have a library called Encoding, which is a library in Coq for doing computable analysis. And the definitions quite closely follow those from computable analysis, with some exceptions to make it a little bit more usable and more practical. But the basic definitions is we use those from computable analysis. And well, one thing about computable analysis is that it's an area of classical mathematics. So it's not using a constructive approach, but Coq kind of has internal logic that is constructive. But it's still kind of, we think that it's kind of the right proof assistant to use for our setting, because in Coq it's quite easy to just define some axioms and then, for example, allow classical reasoning. So we can also do classical reasoning in Coq. And it's kind of good that we have this separation between the internal logic of Coq that is constructive and the axioms that can be added to have some classical reasoning. And well, Coq is also often used in this sense. So in the sense of classical program verification, that we have a program, then so a constructive kind of a constructive part, which is the program. And we have a formal specification that is just a mathematical specification of what the program should do, and some proof of correctness, which usually can use any kind of like normal classical mathematics and doesn't have to be constructive. And this kind of approach is similar to computable analysis. So we think that Coq is quite well suited for this approach. So let me quickly give a few of the main ideas of the library. So the main idea in computable analysis is that, well, as I said, it's an area of classical mathematics. So we assume that spaces like the real numbers and so on just exist in mathematics, and add kind of computable content, or add talk about computability in a second layer. And what that means in Coq. So in our library, we kind of we use axiomatic definitions, so the classical axiomatic definition of the real numbers, for example, which is already contained in the Coq standard library, and then we add computational content by defining a so-called representation. And a representation, so a representation is a represented space in our library. It's just well, it consists of the abstract base type, which can, for example, be the real numbers defined axiomatically, and then a space of what we call names, which are kind of the encodings. So we encode objects from this space by functions from questions to answers, where questions and answers are some arbitrary types in Coq, but they should be, so those questions and answer types should be, so we should provide a proof that they are countable types. So they shouldn't be uncountable. And then what we call the representation is a mapping, so a partial surjective mapping from the space of questions to answers to this abstract space. So what that means is that we have, for example, for a real number or some abstract object, so some other abstract objects from an axiomatically defined space, we represent such an object by a name, which is just a function from that we can ask some questions, some finite questions, and get some finite answer. So maybe this is easier to see with an example. So the kind of standard example for a representation is encoding the real numbers by rational approximations. So that just means we have a function. So a real number is encoded by a function from the rationals to the rationals that gets as input error bound epsilon. And whenever this epsilon is larger than 0, then the condition that this function has to fulfill is that it has to be that the rational number it returns is an epsilon approximation to the real number x. So an approximation with at most error epsilon. And then talking about functions on the real numbers, for example, is done by defining realizers. So realizers are basically just functions that get a name for a real number and return a name for the result of the function. So again, let me show this with an example. So a realizer for addition could, for example, be implemented as follows. We get as input two functions that are names for real numbers x and y. And then what the realizer has to return a function that when given an error bound epsilon, returns an epsilon approximation to the sum x plus y. And it can do so by, well, it's easy to implement something like this in Coq or in some other programming language, because we can just ask our two names for epsilon half approximations of the real number, and then return that, then do some standard addition of rational numbers, and then return the sum. And this is basically the main ideas, what is implemented in the library. And what is done in this work is mostly we discuss things on how to use this for as a basis for exact real computation. So defining some representations for real numbers and realizers for some interesting functions. And well, we also want to compare different representations, and for this we define we kind of define a more high-level structure for computable real numbers, where we just so in this structure we just say we have to provide some realizers for some basic operations, and then we can build more complicated operations with those so build up from those basic operations, and then make the proofs a little bit more high level and easily switch between different representations and so on. So let me just so because time is probably I think I'm already over time. So let me just give you the list of operations and refer you to the longer talk for more details. So the list is just, so we want to have standard arithmetic operations like addition, multiplication, subtraction, and division. Then what is called the efficient limit, which takes a sequence of real numbers, and which takes a sequence of real numbers that kind of quickly, efficiently converges to some limit and then returns the limit. We want some comparison function, and we also want some easy input and output, which is a function that takes dyadic rational numbers as input and transforms this to a name for a real number, and a rational approximation function that takes a real number and a rational number and returns an approximation with this error bound epsilon. So those are the basic ideas, and yeah, so I want to end this talk here, and yeah, thank you very much for listening.
All right, thank you, Holger. Does anybody have a question? You can unmute your audio and ask. Okay.
So, sorry, maybe I have one. Can you say a bit more about this limit operation? I mean, first, how do you represent this infinite sequence?
Okay.
And then how say a bit more about how this works. This looks interesting.
Yeah. So well, it of course it depends on the concrete representation. But if, for example, if we have this representation of rational approximations, so for time reasons, I couldn't go. So in the library, we also have some constructions for example, if we have a represented space for real numbers, we can also get a represented space for sequences of real numbers. And the idea is just that questions now. So for real numbers, the questions were epsilon, and you get an epsilon approximation of the real number. And for the space of sequences of real numbers, you get additionally a natural number that is the index of the sequence element. So you get n and epsilon and return an epsilon approximation of the nth element. And then the efficient limit means they have to so they have to converge with some fixed convergence rate, which we usually just fix to 2 to the minus n. So the nth element of the sequence should be at most 2 to the minus n far away from the limit. And then we can, well, then there are different strategies on how to implement this limit operator. But for this, for the rational representation, it's quite simple, right? We can just take the n+1 element of the limit and return the n approximation with error to epsilon, and then by epsilon half, get an epsilon half approximation, and then get an epsilon approximation of the limit, right?
Okay, yes, thank you.
Thank you. I have a quick question. So Coq is, as you said, has constructive logic as its base system. In your proofs, did you have to assume any non-constructive axiom?
Well, we usually so we kind of So for defining the realizers, we want to be fully constructive because they should basically correspond to programs. So the realizers are those things that work on those approximation functions, and the definition of those should not use any non-constructive axioms. So this should be purely in vanilla Coq, so not using any axioms. But proving the correctness means proving that this actually realizes some real number function, and the real numbers we use are those from the Coq standard library. So they use normal. They are defined axiomatically by the standard axioms of real numbers. So they are not constructed. So we cannot use them for computation, but we use them for the correctness proof of our algorithms.
Thank you. Thank you very much. Thank you for the excellent talk. So I guess we can move on to Peter back.
Okay.
Let's see, Peter. Hopefully
this time.
Yeah. So Peter is going to speak on framework for consistency algorithms.
Okay, it seems that it still doesn't work, so I think Prakash has to take over, but he's also prepared for the talk. So.
Oh. Yeah, okay, so yeah, I can take over.
Okay.
Are you able to hear me?
Yes.
Okay, yeah, so I can.
Can you share the screen? Yes. Good.
Do you see my
Thank
screen?
You. Yeah.
Okay, thanks. Yeah. Yeah, so yeah, my co-author Peter had to give the talk, but now I'll be giving the talk. The talk is Framework for Consistency Algorithm. There are, yeah, so there are a lot of definitions in the title that, I mean, there are a lot of keywords in the title that need to be defined. So we go over it one by one. So I tried to define what concurrency is, what relaxed memory is, and what consistency is. And then we go and look at what the actual problem that we try to solve in the paper. So you might have seen many concurrent programs. Concurrent programs are finite threads that interact through shared variable. So you have a finite set of threads. You have some shared variables which operate on a finite data domain, and they can communicate to each other using these data domain, these shared variables. Of course, the threads can read and write from these shared variables. This is how they communicate. So the memory model actually determines how the threads behave. So we will come to this in a minute. But I mean, assuming a memory model to be an abstract object, a valid execution can be defined as an execution where the reads are consistent and axioms of the memory models are satisfied. And what do we mean by axioms of the memory models are satisfied? These axioms somehow define some optimizations on the memory operations. And if your execution satisfies these axioms, and if all the reads that are in each of the threads are satisfied, then we call it a valid execution according to this memory model, according to the given memory model. Now, this is the model that we are interested in. So we are given a memory model, we are given a set of concurrent programs that communicate, and we want to somehow reason about valid executions of them. Now, example of these memory models are a very basic example is sequential consistency. Sequential consistency is what you would expect a program to behave in a, intuitively. So there are no reorderings of instructions, there are no optimizations, and your threads execute in sequence. That is, any valid execution only requires that the reads are consistent. That is, each reads are essentially the reads are essentially from they are not they don't read some fake values. They read something from the main memory. So here a valid execution is consistency under program order. So each thread program order is satisfied. And what do we mean by consistency? That reads are satisfied. So other way of looking at it is, given a set of executions of thread, or given set of program instructions of each thread, is there a way to shuffle these threads in such a way that each reads are met, each reads are consistent? Or another way of looking at it is there a total order which somehow respects this program order and satisfies each of the reads that occur in the execution? So the SC is good in the sense that it is very close to the intuitive behavior. And the problem with SC is that it can be very slow. For instance, the reads can be very fast, but the writes to be committed into the memory can be very slow. So the solution to this is relaxed memory, in the sense that now you allow some kind of reordering of instructions. For example, we'll come to an example of TSO where the reads can overtake write, roughly. We will come to it in a minute. Essentially, with this relaxed memory, with respect to sequential programs, the behavior essentially is the same. But when it comes to concurrency, with respect to concurrency, things can be very different. So the examples of such relaxed memory are TSO, PSO, alpha, and there are many of them. But in this talk, we'll only be concentrating on TSO. So the main advantage of using this relaxed memory is faster execution. But when it comes to concurrent behaviors, things can go, things need not be as normal as what we would expect it to be. For example, if you take a Decker's mutual exclusion algorithm, run it on an SC, it would guarantee mutual exclusion. For instance, if you run it on TSO, it need not guarantee mutual exclusion. So what are these TSO? TSO stands for total store order. Here the reads on different variables can overtake writes. For example, if there is a read X and a write Y, the reads can essentially go and fetch values before the writes are committed. So if you want to imagine as a machine model, the reads are buffered in order. So if you have a read X, read Y, read Z, these reads are actually put into a cache. And the reads, these writes can be put into a cache, and the reads can actually go to the main memory and pick up values directly, while the writes are still in buffer or still cached. But these writes are in TSO, these writes are buffered in order. That is, they will have to be committed to the memory in the way the programs wrote these values. Now, a valid execution here is whether the reads are consistent under the relaxed program order. So what is this relaxation? We already saw that the reads can overtake writes. So this relaxation is allowed. With this relaxed program order, is there a shuffle of these threads such that the reads are consistent? So this is what we mean by a valid execution with respect to a total store order. So this says that is there a shuffle of relaxed program order with reads being consistent? Or other way of saying is, other way of asking this is there a total order, consistent total order that somehow respects the relaxed program order? So what is the correctness, notion of correctness that we are interested in? Well, if you want a full correctness, you will need to go to the reachability, which essentially is the complexity is not very nice. So we look at a weaker notion of correctness called testing. What is this problem? This problem says that you're given a set of executions of thread, and you're asking whether these set of executions, is there a way to arrange these threads so that you get a consistent valid execution? That is, the reads are satisfied, and the only relaxations that are allowed is the relaxations as allowed by the memory model. So this is the testing problem that we wish to solve. So these kind of problems are very useful in generating test cases. Unfortunately, this problem is NP-complete. NP-complete for various parameters, as we not see, but yeah, but these are NP-complete for various parameters. So what we did in our paper is to identify the source of hardness. So there are two sources of hardness in these problems. One is shuffling of the threads themselves, and second one is something called multiple read from relation. What do we mean by read from relation? So each read can take its value from multiple writes. For example, if I write, one process writes a value 5 to x, another process also writes a value 5 to x. Now, if you have a read x comma 5, this can either map to the process P1 which wrote x comma 5 or process P2 that wrote x comma 5. So there are multiple ways in which these reads can be satisfied. So we looked at a problem where, which we call data independent, which essentially fixed this read from relation. So other way of seeing it is each write writes a unique value. Then your read from relations can be automatically fixed. So we looked at a subclass of problem where the read from relation is fixed or is a priori fixed. So this data independence essentially means that the values written are in some sense unique. So the testing problem now asks whether, given a memory model, given data independent executions of thread, is there a valid consistent execution of these given executions of thread. So one thing that I would like to mention here is this notion of data independence is not new. This has been well studied, and in both in this context as well as in other contexts. Unfortunately, this problem is still NP-complete. So what we did was we tried to do a fixed parameter tractability of this problem. Here we looked at the number of writes as our parameter. That is, we said that give us executions of thread such that the number of writes in these executions is bounded by some k. Now we asked whether this problem is fixed parameter tractable. So what do we mean by fixed parameter tractable? A problem is fixed parameter tractable if it is polynomial in the size of input, but it can be arbitrary in the size of the parameter that we define. So we asked whether there is an algorithm which runs in polynomial in the size of input and some function of k, where k is the parameter. So maybe before okay, there are a few things missing in the slide because this is a bit half-cooked slide. So there is a easy algorithm to get a k power k running time algorithm for this. This is by using the characterization by Jad Algeb and getting iterating over all the total orders possible. What we showed in our paper is that this testing problem can be solved in O star of 2 power k. Here O star is by neglecting the polynomial time. The runtime, which neglects the polynomial part of the running time. So we showed in our paper that the testing problem can be done in O star of 2 power k. And we also showed optimality by assuming ETH. So ETH says that 3SAT cannot be solved in time 2 power small o n plus m, where n is the number of variables and m is the number of clauses. So assuming this ETH, we showed that we can, for every instance of 3SAT, construct an instance of SC, TSO, or PSO with at most n plus m writes. And by this, we also showed the hardness we showed that the problem cannot be solved in time 2 power small o of n plus m, or 2 power small o of k, where k is the number of writes. Yeah, so we showed that SC, TSO, PSO cannot be solved in time 2 power small o of k. Yeah, and thank you. Any questions?
Thank you, Prakash, for that excellent talk. Does anybody have questions? I think you can just speak Okay, so I do have a question for you, Prakash. So in your work, memory model is is one of those three things: SC, PSO, TSO, or do you
Yes.
have a more general framework of specifying memory models?
So we have, I mean, our framework works for SC, TSO, PSO, and alpha and RMO, few other memory models, but we have optimality only for SC, PSO, and TSO. The memory model is somehow part of the, I mean, is given as an input here.
I see.
And
So you
we
mean
have
the
shown that
axioms, the axioms of it are given as
an input, yes.
I see. Okay. Okay, good. Okay, so, okay, thank you.
Thanks.
So let's move on to the next talk by Rebecca. It's on uncertainty reasoning for probabilistic Pertinents via Bayesian networks. Is it Rebecca? Yeah, okay.
Yes.
Yeah, good.
Okay.
I don't know why it says Prakash as on the side. Yeah, but anyway, go ahead. Yeah.
Okay, so okay. Yeah, thank you for the introduction. So the paper that I'm gonna share with you today is a joint work with Benjamin Cabrera, Reiko Heckel, and Barbara König. And it deals with assuming we have a dynamic system that we do not know the state of, and we observe probabilistic information about this system, how can we actually expand our knowledge base given probabilistic information? And so let's start with some motivation. Yeah, given a very big social network, for example, given a very big network, for example, a social network where we have people as nodes and the connection as like friendships or something, we have a state in this system, which is motivated by information diffusion. So we have some piece of information in this network and we don't know the state of the network, which just means we don't know who has this information, but we can maybe observe some transitions. So we assume that we can observe if somebody shares this information, but we don't know who the addressee is, but we might have some probabilistic information about who the addressee is, depending on who this person is friends with. So yeah, we have a dynamic system with incomplete knowledge about its state. We assume that we have complete knowledge about the structure of the system, but just the state is incomplete. And then we observe probabilistic information. So we see that somebody, as I said, sends a message, and now we have to update our knowledge base by incorporating this information. And at the end, we of course want to reason about probabilities. So we want to be able to answer questions about the state of the system. For example, if a certain person now knows an information, or how likely it is that some person knows the information. So to do this, we need, firstly, we have to efficiently store probability distributions. And also we need an update mechanism for this, for these probability distributions, because we gather information, probabilistic information, and we have to have an update mechanism, and this will be local. And at the end, we want to have a suitable evaluation mechanism, and for that we use the well-known method of variable elimination. So our paper and my video was structured into these three main parts. The first one is discussing the dynamic system that we looked at, and we looked at condition event nets with uncertainty. So a condition event net is basically a Petri net where, where each state can only have up to one token. So it's either it has a token or it doesn't have a token. And we don't know the marking, but we have a probability vector over the marking. Yeah, so this is the dynamic system, and we can just translate this into this social network example that I just explained to you, where we have a state for each person, and if the state is marked, then this person knows the information, and if it's not marked, then the person doesn't know the information. And of course, if somebody has this information, it can also spread it to his or her friends. And this is the dynamic system that we observe. And every time a transition is fired, we get information about which transition could be the one that fired, and we get some probability value assigned to the transitions. And now we have to update our knowledge base. And for our knowledge base, we use a modification on Bayesian networks, because in Bayesian networks, you have the variables are locally dependent, and you don't have like this global thing, but you can actually split it up into the variables itself. And so if somebody sends a message in our example, we only have local changes because probably the person is not friends with the whole network. So we only have to incorporate local changes. So we actually exploit the network structure that is known to us in order to allow for these local updates to our knowledge base. And for that, we use Bayesian networks. But because Bayesian networks are a static thing, we have to use modular Bayesian networks, which actually allow us to extend a Bayesian network to further extend our knowledge base. And then at the end, we also need an evaluation mechanism. And for that, like I just said, we use variable elimination. And that is also a well-known method to evaluate Bayesian networks. And we had to modify it a bit to use it for these modular Bayesian networks. And it is based on tree decompositions. And because we have a simulation, we actually approximate like a good elimination order, because it's an NP complete problem, I think. Yeah, so yeah, like I said, we also simulated this, and it's available open source on GitHub. And these are some runtime results. So here we compared the median runtime of our system, which is the MBN, so the blue line, which is fairly linear. The runtime is fairly linear, and the naive simulation using joint distributions is exponential, because there we don't have the advantage of using these local updates. We have to update the whole knowledge database, more or less. Yeah, and here you can, and for this we generated random Pertinents with a certain number of places, and the more places you have in the Pertinet, the more variables you will have, and it scales exponentially for joint distributions. Yeah, yeah, and that's it. So now you can ask questions, and I'll be happy to answer.
Thank you, Rebecca. So questions for Rebecca?
Rebecca, Madhavan here. So I didn't exactly understand the firing rule for your probabilistic, your conditional event systems.
So can you repeat the question?
Yeah, so I didn't understand the firing rule for markings, when transitions are enabled, how the probabilities are updated after a marking, a probabilistic marking. Like when a transition happens, how do the probabilities get updated to the?
Mm-hmm. Yeah, okay, so in this example, we say that we have like a list of transitions that could have fired, and they have an assigned probability, and then we use that and build like a matrix, a substochastic matrix out of it, and we use that and add it to this Bayesian network. So to really understand how the modular Bayesian network works, it would be too long to explain here, but it's basically a kind of a Markov chain, but split into like smaller Markov chains and then put together to actually have this local property. So it's matrices, and we multiply matrices.
Okay, thanks. Maybe I'll go and look at the paper and try to get this.
Any other question? Rebecca, I do have one question for you. So you have this graph. So you said in the graph you generated random Bayesian networks, and you transformed them into Bayesian networks, modular Bayesian networks. So what is the complexity of this transformation?
So we generated random Pertinents.
Random Pertinents.
Yeah, random Pertinents. And for the Bayesian networks, we actually it's a separate thing, and we just and in the beginning we have a distribution where every place could be marked or not marked, so it's a half, and then we just add on our new matrices that we get from observing the transitions. So there's no actual translation from a Pertinent to a Bayesian net, but the Bayesian net is used to store our knowledge and update our knowledge. Yeah.
Okay. Any other question? Okay, thank you, Rebecca. We can go on to the last talk, and we seem to be on schedule. So I guess it's Cyan who's going to speak next?
Yeah.
Okay, Cyan.
Hi. I'll just share my screen.
Yeah. It's going to speak on reachability for updatable timed automata made faster and more effective.
I hope you can see my screen, full screen.
Yes.
Okay. So yeah, thanks for the introduction. So this is a joint work with my supervisors, Paul Gasta and B. Srivatsan. So in this talk, I'll go over these 4 things and also talk a little bit about what exactly we have done in this work. So what are updatable timed automata? So updatable timed automata are an extension of classical timed automata. So like classical timed automata, we have guards where you can compare a clock with a constant. Now, additionally, we have something called updates. Now, in classical timed automata, we have resets where in one transition, we can set a set of clocks to 0. Now here, you can set a clock X to the value of a clock Z plus D. But the Z is any clock, it can possibly be X as well. And D is any positive or negative integer. So in this example, the Z is actually X and D is equal to -1. Now, the problem that we consider on this model is the classical problem of reachability. So this problem asks that given an updatable timed automaton with a few labeled states, are any of these labeled states reachable from the starting state? Now, it was shown in this paper that this problem is in general undecidable. However, there are several decidable subclasses of updatable timed automata. Now, the way this decidability was shown is using something called regions. But in this work, we don't focus on that method. Instead, we focus on a method based on something called zones. So I'll just give a brief idea about how this framework works. So the reachability using zones is based on 2 steps. The first step is a static analysis on the input. And in the second step, we build the zone graph. Now, this building zone graph requires a simulation relation to be defined. Now, in our previous work, we have defined a simulation relation that works for updatable timed automata. Now, this particular simulation relation is parameterized by something that we call a GMAP. And in the static analysis part, we essentially compute this GMAP. So given an updatable timed automaton, the reachability procedure works like this. So it first computes the GMAP corresponding to this automaton, and then it builds the zone graph using the simulation relation that we get out of this GMAP. Now, what is this work all about? So in this work, we focus on the static analysis. Now, before I go into details about our work, let me first say what is this GMAP. So GMAP actually assigns a set of atomic constraints to every state of the given automaton. Now, how do we compute this GMAP? We do it using a fixed point computation. Now, for certain examples, this fixed point may not terminate. Say, for example, so I'll tell you how this GMAP is computed. Suppose we have one transition like this in the automaton from Q1 to Q2 where the guard is G and the update is up. Then since we have two states, we have two sets, G of Q1 and G of Q2. Now in the first step, we add the guard to the G of the source. So in this case, we add the G to G of Q1. Now suppose we do it for all the transitions and then we get in G2 these constraints, and in G of Q1, suppose we get these constraints. Now once this step is done, then for every transition, we see the constraints that are present in G of this. So for in this case, suppose this phi1 to phi-m. And for each such constraint, we propagate a new constraint, which we call the pre of phi1 and up, and we add it to G of Q1. So like this, all these will also be added, and for phi-m also be added. Now this is what we did in our previous work. Now in this work, we replace this pre of phi1 up with a new pre function, that is pre of phi1 G up. So the thing to note here is that now as argument, we have the guard present in the constraint, which was in the transition, which we did not have previously. So similarly, this pre also gets replaced with this. So just to summarize, the main change that we have in this work is we replace this pre of phi comma up with pre of phi G and up. Now what is the gain that we get is for a lot of constraints, this pre of phi G up turns out to be the trivial constraint true. And in this case, we don't have to, because it's true, so we don't have to propagate this. So we have lesser propagations than what we had before. Now this has two effects. First, it makes our previous algorithm faster, and also the G computation, which may not terminate in certain examples, it makes it terminate for a larger class of automata. So I'll just briefly explain this. So since now we have lesser number of constraints that get propagated, the ultimate GQ sets that we get at the end of this computation are smaller. Now this implies that the simulation check that we use while building the zone graph, this check becomes faster, which results in the overall reachability algorithm becoming faster. Now also, since now we have lesser number of propagations, the constraints that would have been added don't get added now, and it stops the further propagations. So in some of the examples, this fixed point computation terminates now, which was not terminating previously. Now this class includes this class called timed automata with bounded subtraction. Now this class is important because this is used to model preemptive scheduling. So I won't go much into details in this talk, but we have some prototype implementation of our algorithm in a tool called tchecker. So tchecker is a open source tool for model checking timed automata. And these are the results that we get. So the main things to note here is that in this blue part, so these are all examples of schedulability. Our old fixed point computation does not terminate in any of these examples, whereas the new one terminates. And in this red part, as we can see, so this is not a schedulability example, but in this case, our new algorithm takes lesser time than the previous one. Now, with this change, we also get a challenge, which is now it is more hard to check, given an automaton, whether the GMAP computation is going to terminate or not. So earlier we could check this in polynomial time. So now it becomes pseudo polynomial time. So it's polynomial time when the constants are written in unary, and it is p-space when the constants are written in binary. So it is actually p-space complete in this case. So yeah, so this is essentially what I wanted to talk about in this short talk. And yeah, so I said what are updatable timed automata. I also said the basic framework of checking reachability using zones. I said a little bit about what we did. So we essentially replaced this pre and we added the guard while computing the pre, and this results in lesser number of constraints getting propagated. Now this results in, it makes the overall reachability faster by making the simulation check faster. And also it makes the fixed point computation terminate for a larger class of automata. So yeah, that's all I had to say. So yeah, thank you.
Thank you, Cyan, for that excellent talk. Questions? Any questions?
Maybe I have one question.
Sure, Barbara. Yeah, go ahead.
Yes, I was wondering, I mean, you kind of made the fixed point iteration more efficient by doing some tricks. I wonder, are these tricks specific to this type of automata, or maybe can they also be used for other types of automata?
Well, so I don't know. I hope it can be used in other cases as well. So yeah, but I don't have any examples like in any other model where I can say that it is going to work, but yeah, possibly it can be used. Yeah.
Mm-hmm. Okay, thank you.
Any other question? Sen, I had a question for you. So there was something about p space complete and p time.
Yes, yes.
So is that p time complete and not, or is it just p in p time?
I guess it's p time complete. Yeah, it's
Okay.
p space complete as well.
But you haven't proved this p time complete. It's not like log space complete or something.
No, we have given an upper bound. I believe it should be complete as well. Yeah, but okay. Yeah.
Okay.
Yeah.
Okay. Thank you.
Yeah. Thank
I
you.
guess that concludes this session, and thank you for all the speakers for the excellent talks. It's a good session, and thank you for everybody for participating. So I guess we can end the session here. Okay. Thank you.
Thank you.